Hello everyone, welcome to a new lecture in the series of Deep Learning for Control. In this lecture, we will be discussing state space neural network or SSNN, which are a particular class of recurrent neural networks used for representing state space models. State space models are important in control systems since states captures the internal behavior of the system. This means that state space models capture the complete behavior of the system, whereas input-output model only captures the input-output behavior, which may only capture the partial system behavior based on which inputs and output are being considered. This also implies that stability of state space models establish the internal stability of the system, which means all the dynamic variables in the system has a stable nature. On the other hand, stability of input-output models only guarantee the stability of output variables, which leads to the possibility of some of the internal variables that does not have an influence on the outputs can have an unstable behavior. Due to these reasons, modern control approaches such as MPC, adaptive control, etc. mostly use state space models. In this lecture, we will discuss how we can learn state space model from data using neural networks. Here is the overview of this lecture. We will start with an introduction to state space neural network or SSNN. Next, we introduce the idea of ordered variants in the SSNN, which leads to SSNN with ordered variants or SSNNO, and we discuss its application in MPC. In general, a state-space neural network or SSNN can be used for approximating discrete-time nonlinear system represented in state space as in equation 1, where xk is the state vector, uk is the control input vector, yk is the output vector. F is a nonlinear function which maps the current state to the next state, and h is another nonlinear function which maps the current state to the current output. Here we can see that this h is like a static nonlinear function, and this f is a dynamic nonlinear function. Then in SSNN, the state and output functions are approximated by NNs as in equation 2, where this FNN is an approximation of the function f, and it can also have an approximation of some transformation of the function f since the states are not unique. And similarly, HNN will be an approximation of the function h. And state and output neural networks can be represented as deep neural networks as in equation 3, where the state NN containing L number of layers and the output NN containing H number of layers. And this figure shows a schematic representation of the SSNN, where we have FNN is associated with a recurrent connection. FNN takes the current input UK and the current state estimate xk hat to find the next state estimate xk plus 1 hat. By shifting it by one instant, we obtain xk hat itself. And then from xk plus 1 hat, we get yk plus 1 hat as the predicted output. SSNN is one popular version of the recurrent neural network, and it is also commonly called as the RNN itself in many of the literature. Now, the input-output data for the SSNN is similar as in the previous lecture, which consists of capital D samples of the input vectors and output vectors. Now, using the input data and also an initial state estimate, which is denoted by x0 hat, we can find the predicted state for all the D samples. And using the predicted state, we can find the predicted output as in this equation. This combined equation we can represent using a function fyp, which takes the initial state estimate x0 hat and also the parameters of the state and output nn. Once we define these things, we can find the predicted state and output sequence for a control input sequence. And then the loss function for SSNN can be defined as in equation 6, which consists of the prediction of all the D samples. And this y hat, we can represent it as fyp of x0 hat, theta f and theta h. Now by taking all these parameters into a parameter vector theta, we can define the optimization problem for SSNN to find the optimal parameter theta, which minimizes this loss function. Next, we move on to the SSNN with ordered variants, in which we introduce a regularization term similar to AEO to achieve ordering in the state space. Here, the state and output functions are similar to SSNN. The loss function is modified to include a variance regularization term. Here we have this first term is the output prediction error term similar to the standard SSNN, and it is denoted by JY. And the second part is the state variance regularization term, which is the main feature of this SSNNO, which is denoted by JV. And the third part is basically the parameter regularization term, which is denoted by j theta. Here this jv can be expanded as some constant into w1 times the variance of x1, wd times the variance of xd. Here we consider d as the dimension of the initial state vector in the SSNNO. Here this w is the matrix which contain all the scaling factors w1 till wd, and by suitably selecting the elements of w, we can achieve ordering in the state space. So let's say if we are selecting this w in an increasing order, it means like the w1 is the smallest and wd is the largest. We can arrange the state variance in decreasing order. In other words, x1 will be having the largest variance and xd will be having the smallest variance. In many of the practical cases, the variance of the last few variables can have 0. This is particularly obtained when this d will be larger than the actual system order, small letter n. This is based on the fact that we only need n state variables to fit any data set generated by an nth order system. And sometimes we can also have model order reduction, where we only require lesser than n number of state variables to fit the data. The optimization problem for the SSNNO is to find the optimal parameter theta, which minimizes this loss function. And after solving this optimization problem, the predicted states using the SSNNO model will be ordered in decreasing variance. And for the last few state variable, we may having negligible variances. Based on that, we can also estimate a model order by identifying the number of state variables for which the variance is greater than the threshold delta. And here we can identify a reduced order model by replacing the states with negligible variance or like zero variance with their mean values. When we replace those variables with their mean values, that term basically becomes a constant term, which will reduce the order of the identified model. And here is a theoretical statement which guarantees ordering with the SSNNO, which says that the global optimal solution to the SSNNO training problem results in a model which satisfies this variance ordering. So the first variable will be having the largest variance and it will be ordered in decreasing manner. And similarly, the degradation performance due to the regularization term can be bounded by a parameter lambda, where epsilon is the bound for the output prediction error with the standard SSNN. And with the SSNNO, the bound will be the epsilon plus lambda, where lambda is a user-defined tolerance. So this theorem says that if we select any particular tolerance, lambda greater than 0, we can able to find an SSNNO for which the optimal value of the prediction error will be bounded by epsilon plus lambda. And next we move on to the SSNN based data-driven MPC, where we have the steady state criteria as equation 15. Here we use the predicted state and predicted output equation, which will be same as the state reference and output reference. Here we don't need a hat, so it is XR. And by substituting the SSNNO model here, we can obtain the steady state equation as equation 16, which can be solved for obtaining the state and control reference, XR and UR. In general, the YR is assumed to be known, and we have to solve this equation for finding the state and control reference. The optimization problem for SSNN based NMBC can be obtained as in equation 17. The derivation of this problem is given in the data-driven MPC lecture series, for which the link is given in the description. Here we have the algorithm for the data-driven NMPC using state-space neural network, in which we have the original input and output data is assumed to be available. And we have to select the number of layers in the state and output network, and also the number of hidden layer neurons. Then once we define the structure of this SSNN, that will decide the size of the initial parameter vector. And we can initialize this parameter vector as a Gaussian random vector. Then solve the optimization problem for SSNN or SSNNO to find the optimal parameter vector. Once the model is identified, we can define the parameters for the MPC, such as the prediction horizon and the weight matrix for the state and control vectors. And we can also find the state reference and control reference by solving the steady state condition. After that, we can solve the MPC optimization problem at each time instant to find the optimal control sequence from which the first element is applied to the system. So next we move on to the simulations of the SSNN. Here we consider CSTR system similar to the previous lecture, and the parameters are chosen as in equation 19. Here we have the training and testing response with the SSN and O, where we can see that the training input have sufficient number of perturbations to capture the dynamics of the system. Here we can see the actual output in red color and the predicted output using SSN and O in green color. And we can see that the predicted output is capturing the actual behavior in the system. Here we can have the performance comparison for SSNNO and SSNN, where the state variants are shown in the first 3 rows. And here with SSNN, we do not have an ordered variance, and the variances are also non-zero for all the 3 states. Whereas for SSNNO, we can see that the variances are ordered, and for the last state, the variance is nearly 0. It implies that the actual order of the system was 2, so that's why we only have 2 states with somewhat significant variance. Here, if we select the variance threshold as 0.005, we can obtain a reduced order SSNNO model with order 2. Since this variable will not satisfy this threshold, so this third state will be replaced by its mean value. And by doing so, the prediction array still will be almost same as the third order model, which we can see from here. And another observation is that here the second state also have small variance. Therefore, if we use the variance threshold of 0.001, this one will also becomes a residual state. And if we replace these 2 states with its mean value, we obtain a first order reduced order model, for which we have only one state with this variance. And for this particular model also, we can see that the prediction error is almost same as the third order model. So this particularly means that using the SSN and O, we can achieve ordering in the predicted states in terms of variance. And another observation, this ordering can be effectively utilized for determining the model order, which can also result in model order reduction if properly designed. Next, we consider the data-driven NMPC, where we use the SSNN model, and the system considered is the CSTR system, and the simulation parameters are chosen as in equation 22. Here we have the training input and output as shown in this figure, and here we can have the output with data-driven NMPC, where we can see that the output is able to follow the reference. And the figure C shows the control input, where we can observe that it is satisfying the constraints. To summarize, we can use either SSNN or SSNNO model for identifying state space model from input-output data. And these models are particularly useful in modern control approaches such as MPC and adaptive control. That leads us to the end of this lecture. Thanks for watching.